Today we will discuss the topic forced harmonic vibration in vibration engineering. In forced harmonic vibration, that is 2 degree of freedom system, we talk about the forced harmonic vibration in 2 degree of freedom system, in which there are two bodies that is shown in the diagram. Mass of first body is m1 and second body is m2. A force F sin omega t is applied or acting on the body first, which is shown in figure, and K1 is the stiffness for first spring, and for second is K, and next is K2. The equation of motion can be written as m1 x1 double dot plus K1 plus kx1 minus kx2 is equal to F sin omega t, and the next equation for the second m2 x2 double dot plus k plus k2 x2 minus kx1 is equal to 0. We have to find the solution of this equation. Let us assume the solution of this form is for x1 is equal to a1 sin omega t plus phi, and for x2 is equal to a2 sin omega t plus phi. If we differentiate this equation for x1 x2, we get the x1 dot and x1 double dot, x2 dot and x2 double dot, that is the acceleration vector and velocity vector. If we put these values in the equation 5.6.1 and 5.6.2, then we get k1 plus k minus m1 omega square into a1 minus ka2 is equal to f minus ka1 plus k plus k2 minus m2 omega square into a2 is equal to 0. By solving this equation, above equation, that we find the value of a1 a2, in which a1 is equal to f k2 plus k minus m2 omega square upon k2 plus k minus m2 omega square, k1 plus k minus m1 omega square minus k square, and the value of a2 is equal to fk upon k2 plus k minus m1 omega square, k1 plus k minus m1 omega square minus k square, that is the value of a2. The denomination of equations, that is 5.6.7 and 5.6.8, these are shown in the form of amplitude, are same as the equation 5.3.7, which we have discussed earlier. Thus the denominator of the said equations is the frequency equation itself. The denominators become 0 when exciting frequency is equal to the natural frequency of the system, where omega 1 is equal to root k by m, or the omega 2 is equal to root 3 k by m. It is evident that the amplitudes of vibration a1 and a2 are infinite when denominators in equations 5.6.7 and 5.6.8, that is the A1 A2 equation are 0, it means when exciting frequency is equal to any of two natural frequencies, resonance in the system will occur. A1 becomes 0 when k plus k2 is equal to m2 mega square. This gives the value of 0, which is taken with the help of equations 5.6.7. A for A1, thus it makes M1 stationary. While this type of expression is not possible for mass M2, a little consideration shows the mass M1 has been initially excited by the force and under certain assumptions it is motionless, while mass M2 has some motion. In matrix form we can written as the following. You can see that is the matrix method. Now we talk about the semi-definite system. That is the system having one of their natural frequencies equal to 0 are known as the semi-definite system. The example of this type of system is shown in figure, that is the mass m1 m2 and the displacement for m1 is x1, for m2 is x2, and both masses are connected with spring that having the stiffness k. For this, the equation of motion can be written as m1 x1 double dot plus k x1 minus x2 is equal to 0, m2 x2 double dot plus k x2 minus x1 is equal to 0. In case of free vibration, let us assume the motion to be harmonic. In case the value of amplitude x1 is equal to a1 sine omega t plus phi, and x2 is equal to a2 sine omega t plus phi, where we can find the velocity vector and the acceleration vector in the form of x1 dot, x1 double dot, x2 dot and x2 double dot. These values we put in this equation, that is 5.7.1 and 5.7.2. Then we get k minus m1 omega square into a1 minus k a2 is equal to 0, and second minus k a1 plus k minus m2 omega square a2 is equal to 0. By solving this equation by the matrix method, that gives m1 m2 omega 4 minus k m1 plus m2 omega square is equal to 0. By taking common omega square, that is in bracket m1 m2 omega square minus k m1 plus m2 is equal to 0, where the value of omega 1 is equal to 0 and omega 2 is equal to in root k m1 plus m2 upon m1 m2. This equation, that is 5.7.9, we can see that one of the natural frequencies of the system is equal to 0. The system is not oscillating. There is no relative motions between m1 and m2, and it can move as a rigid body. That is all about the forced harmonic vibrations and semi-definite systems. Thank you.